there might be another layer of reality under the reality we know. So there are people who just, but in fact, by studying the electromagnetic waves trapped inside heated cavities. And Einstein himself worked on the difference between wet and dry sand, on a new kind of refrigerator, etc. And in fact, an oil company paid me a lot of money. Many, many years ago, they paid me a lot of money to study Einstein's paper between the wet and dry sand. And you guys cannot guess why oil company would be extremely interested in Einstein's paper. So these oil engineers, petroleum exploration, they never heard of general relativity or special relativity or whatever. But they are very interested in the quality of Einstein's paper on sand. So, of course, I'm also familiar with Phil Anderson's More is Different. And certainly nobody would dispute this. So Phil Anderson, in fact, I know him quite well. He was, at one time, my colleague at Princeton, and then later, this thing keeps falling off, doesn't work very well. And later, he was chair of the board at the Institute for Theoretical Physics in Santa Barbara. And so he always reminded me that he was the one who hired me. So certainly, I don't disagree with Anderson, and certainly nobody would dispute this. And of course, knowledge of quarks does not help you to understand how water becomes translucent solid at low temperatures, right? But in this book, and here now in this talk, I want to discuss the foundational ideas and not this and that. So I also am going to restrict myself to only long-established and empirically verified ideas. Hence, I will say nothing about string theory or quantum gravity. Okay, so what is the most important foundational idea that, in fact, made physics possible? Oh, I also wanted to, before I say this, just to appease some of the physicists in the audience, that I'm also more than sure that many physicists, if asked to list the top 10 foundational ideas, would no doubt produce lists that differ from mine, not enormously, I should hope. But all I can say is that my list reflects my own journey in theoretical physics, my education, and those who influenced me. And a book of this kind is necessarily and preferably unapologetically opinionated. You don't want to read a book without strong opinions. So 10 is, of course, an arbitrary number, an evolutionary accident on our particular planet, a mere convenience. So 10 is meaningless. You could, of course, add or subtract. So let me start with the most important idea of theoretical physics, which is that the most incomprehensible thing about the world is that it's comprehensible. Einstein, again, he said this. So this is perhaps the most original and creative idea that the human race, the entire race of humans, ever had. And it's no doubt it was rejected by every referee of every journal that it was submitted to. Okay? So somebody had the idea that the world is actually comprehensible. And very few humans, very, very few, a handful of Greeks, perhaps a few Babylonians also, I would say. But as far as I know, it was never clearly articulated in most ancient civilization. So in particular, I had some very interesting discussions in China a long time ago, especially at Tsinghua University with Kong Liang and others, about why the Chinese never thought that the world is actually comprehensible. Now, of course, the Chinese had technology and some disconnected empirical knowledge, without logic and without an overarching system. And in spite of Needham, I don't think this suffices. So it's this handful of Greeks that set our worldview, and they are totally outliers. Now, there are plenty of questions, of course, that are beyond the comprehension and grasp of physics, of course. So, for example, it's another level of existence that we know nothing about. You can make up your own questions, of course. Now, why should nature be comprehensible? By the mind of these creatures that evolved recently on a dust mite of a planet orbiting an insignificant star, drifting in a far from prestigious neighborhood of a mediocre, average-looking galaxy. So why should the laws of physics be simple and beautiful? We could have found ourselves living in an intrinsically ugly universe, a chaotic world, in no way graspable through thinking. As Einstein, again, it was Einstein, I'm quoting him here, put it. Now, the other view is that perhaps only that which we can comprehend is comprehensible. Okay. So, okay. Number 2 on my list, that the laws of physics are the same here, there, and everywhere. The same yesterday, today, and tomorrow. So from day one, the entire human race, for example, had looked up at the ethereal moon floating up there, all the while waxing and waning like the tides. But after so many millions of human beings, Newton alone realized that the moon was actually falling. And not only that, but the falling moon and the falling apple are governed by the same laws of physics. Okay? That laws are universal and eternal. And so before Newton, there was such a thing as terrestrial mechanics and celestial mechanics, that the laws of physics might be different on earth and in heaven. So after Newton, astrophysics and cosmology became part of physics. Now, of course, the laws of physics could be broken, either explicitly or spontaneously. We all know various breaking of physical laws that physicists long believed to be true. And we all know that in the 1950s, physicists were shocked by the discovery that the weak interaction distinguishes between left and right. So I have this, I found this photo and I use it in my book. And the caption of this photo in my book is the Swedish folly. Because of these 3 young people sitting at dinner at Berkeley, only the person who made the least, by far the least contribution to physics got the Nobel Prize. So you all know what happened, right? That he's the one with the Nobel Prize and not the others. So the statement is, of course, that I made, is of course subject to being disproved. Physics is empirical science. But thus far, the evidence in favor has been exceedingly good. It's constantly being tested. Okay. Now, the third idea on my list, is that the world is quantum. Now, I give you a few familiar quotes. Quantum mechanics makes absolutely no sense, from Roger Penrose, who kindly wrote the preface to my book, to one of my books, and Niels Bohr, that those who are not shocked cannot possibly have understood it, and John Wheeler, if you're not completely confused, you do not understand it, and so on and so forth. And indeed, some of us in this room could have said something similar as students. When I was a student, certainly thought that quantum mechanics makes no sense. But in my generation, in the United States, we belong to the Feynman School of Physics, which is this famous quote, misattributed to Feynman, which is, shut up and calculate. Okay? So when I was at the university, if you ask any questions about quantum mechanics, you'll be told to shut up and calculate. Okay, so that's the... I'd like to talk a little bit about quantum mechanics and in particular also Bell's inequality. Now, I tried to read Bell's book about 20 or 30 years ago, and I find it very difficult, because there are a lot of words in the book that I don't understand, such as reality and elements of reality and so on. So I prefer to follow the Italian physicist Marconi. I like his treatment. And in his paper, he said that he doesn't want to use words like reality and words like that. But he used counterfactual or prefactual definite. I prefer prefactual definite, prefactual definite. Now, classical physics is prefactual definite, but quantum physics is not. Now, what does that mean? Suppose we have a weirdo nerd friend, and in the physics department, you can find a lot of weirdo nerds, for sure. For some unfathomable reason, he refused to reveal to us the color of a scarf he owns. He said he has this nice scarf. But instead, he asked us to guess, saying there's 70% chance that it's blue, 30% chance that it's red. But we know that even though we have never seen it and we don't know the color, that his scarf is a definite color. And that's what we mean by reality. And since he knows the color of his scarf, this is what I said in the book, this use, or rather abuse, of the word probability in everyday life is just to tease us into guessing the color. So this is like typical, maybe not in China, but in the United States, when you walk into the Physics Institute on Monday morning, somebody on the secretarial staff might say something like, "Hi, Tony, guess what I did this weekend?" Okay, so that color exists independently of the observer is what we might call real. And no one besides a true crazy, right, people that should be locked up, would say in daily life that the color of our friend's scarf is a meaningless construct until we actually see the scarf. So whatever our weirdo friend actually did on the weekend could not change by the time he asked us on Monday morning to guess what he did. Right? So that's what I mean by reality. So Bell's inequality, now that I finally understood it, it's actually a statement about classical physics. And according to the French guy, Michel Le Berlac, it actually goes back to the English logician in the 19th century, George Boole. So it's merely a Boolean algebra. And here I don't have time to discuss in detail, but we make a truth table of various colors and fabric, and whether it has tassel or no tassel, the probabilities, some probability you can define has to be greater than 1 in classical reality, in the classical world. So you don't even need to know any quantum mechanics to understand Bell's inequality. Bell's inequality is actually it's a misconception by a lot of people walking around in the streets that you need to be an expert on quantum physics to understand Bell's inequality. So actually, according to my friend Michel Le Berlac, he's actually a 19th century British inequality. Some of you may wonder who is Michel Le Berlac. Well, he happens to be the French translator of one of my books, so that's how I know him. Number 4 on the list of the top 10 ideas is quantum fields and Einstein's total love. And now we understand our universe consists of a web of interacting quantum fields. And each of these tells the others how to dance. So let's go back to the late 1920s. Quantum physics in the late 1920s, the electromagnetic wave was treated as a relativistic field, while the electron was treated as a non-relativistic particle. And Dirac found the equation for a relativistic electron, and then Pascal Jordan, or as Americans pronounce it, Jordan, convinced Dirac that the electron should also be treated as a field. And apparently Weinberg told me that the textbooks often got the history wrong. They felt textbooks often, including my own textbook on quantum field theory, to say that Dirac proposed that the electron should be treated as a field. And apparently Dirac resisted the idea, actually. But this is a true watershed moment in physics, in my opinion. Henceforth, everybody is a field. Okay. Nobody. In quantum field theory, you have beautifully elegant explanation of very simple things. One of the most profound questions in physics, which I did not understand when I was an undergraduate. Why are electrons identical? There's zillions of electrons in the universe. Why are they the same? If you ask your professor, if you are an undergraduate taking a course on non-relativistic quantum mechanics, you can ask your professor this question. There's no answer in quantum mechanics. There's total fact. It's a fact. Okay? And in theoretical physics, we like to keep the number of facts to a minimum. So why are all the electrons identical? So quantum field theory provides an elegantly simple answer to this question, because there exists only one electron field, and the zillions of electrons we encounter in the universe are just excitations in this one single field. Now, Oppenheimer, who has become extremely popular now because of the movie, everybody and his grandmother knows Oppenheimer. When he was writing, he was writing just a few months before he died. And he said it was Einstein's total love of the idea of a field that made him know that the gravitation has to be a field. So, number 5, symmetry. A universe full of symmetries. The notion that somehow our universe are symmetric, that fundamental laws are somehow symmetric. And in fact, you could say a central theme of 20th century physics has been the appreciation and discovery of ever larger symmetries. So, in the 19th century, when mathematicians invented group theory, some of them actually said, this is something, we finally invented something that physicists cannot steal and use. But of course, nobody knew about quantum physics. It's quantum physics that exalted group theory, because quantum physics has a superposition principle. Classical physics doesn't have superposition, so you cannot really use group theory. Here's a really astonishing fact that the historian of physics, Peter Galison, told me. He showed me a paper by Gerald Houghton, who's a very famous historian, another famous historian at Harvard. He was already an old guy when I was a student. He examined an encyclopedia of physics from the late 1920s, and there was only one mention of symmetry in the whole book. And it just says that Einstein's metric tensor is symmetric, and the interchange of the indices is trivial. So in the 19th century, there's no reference to symmetry in physics. The only references are to crystals. So this is a very little known fact also, that Wigner did a great thing, that by introducing group theory into quantum physics. After he got his degree in Berlin, in Germany, he went back to his father's leather factory in Hungary. And he was very unhappy. He wrote that he felt that if he was going to spend the rest of his life making women's purses and shoes for men, he would go crazy. So he asked his father if he could go back to Germany to apply for a job. And completely by chance, for the history of physics, the job was as an assistant to a crystallographer. And so Wigner managed to introduce group theory into physics. And when he did this, Schrödinger told him, come on, this kind of mathematics, nobody would be using group theory in 5 years, right? So Einstein said the same thing. And so Wigner said, I told von Neumann, And von Neumann reassured me, oh, these are old guys, the old fogies. In 5 years, every student will learn group theory as a matter of course. And of course, he was right, because I've been teaching group theory to undergraduates for almost 10 years now, and I've written a textbook on group theory. So every undergraduate in Santa Barbara is supposed to have learned group theory. So nature in the 20th century span a surprise, a vast internal space from SU2 to SU3 and M2 quarks. And the number and properties of hadrons are carved in stone by group representation theory. And then, of course, this all then eventually led to Yang-Mills theory and color. So I want to show that, just for fun, I want to show a picture of Gell-Mann, because here is a photo of him with his last girlfriend before he passed away, and whom my wife knew. Anyway, so in this effort towards logical beauty, Einstein said that spiritual formulas were discovered. And he was referring to Noether's theorem. And here's Noether. So one of the great mathematicians who contributed to physics, she discovered, as I think everyone in this audience knows, that the conservation laws of physics originate in symmetries. So we now know, I already mentioned things are conserved, right? So energy is conserved, momentum is conserved, etc., etc. But where do these conservation laws come from? So when I was an undergraduate first learning about physics, if I ask my professors, why is energy conserved, the professor cannot tell me, okay? Unless he knows Noether's theorem. So this is one of the great contributions from mathematicians into physics. And Einstein called it a spiritual formula. Now, if any of the students here ever discover a formula that Einstein would consider as spiritual, I think you've definitely made an important contribution. So, number 6, like top 10 ideas. I now come to number 6 on my list. The number 6 is Einstein, whom I call the exterminator of relativity. He got rid of relativity. In fact, if you look at Einstein's original paper, 1905, you will never see the word relativity. This very unfortunate term, the theory of relativity, was actually coined in 1906 by a totally unknown German physicist named Alfred Bucherer, who is now long lost in the dustbin of history, as the British would say. And is possibly an anti-Semite. I'm not a historian, so I'm not verified that he was an anti-Semite and that he was using this term to attack Einstein. But later in life, Einstein regretted not calling invariant theory, because the whole point of Einstein's theory is that things are not relative, that things are invariant, that different observers see the same truth. So I, on the other hand, had some very unfortunate encounters with a philosophy professor who told me that you physicists have proved that truth is relative. So if Einstein had called it invariant theory, I wouldn't have to waste my time explaining this. So, in fact, philosophers somehow like my books, and I've been invited to conferences on philosophy. But in fact, one philosopher last year came to Santa Barbara to see me. And I said, why do you want to come, fly halfway across the country? And in all my books, I make fun of philosophers. And he said, no. You and Feynman both make fun of philosophers, but in such a way that actually that make yourselves, actually what you say is in some ways philosophical. So Einstein actually struck back. And he said, I'm convinced that philosophy has had a harmful effect in the progress of scientific. He laughs. But however, and this is particularly true of our concepts of time and space. But by the way, if you read about Einstein, what he was even more incensed, which is he was even angrier. Philosophers didn't make him really that angry, but the people that really made him angry are the art critics. And the art critics refer to him as the father of Cubism, that he's the one who inspired Picasso. And this is total nonsense. Anyway, now when I give this talk, and this book is supposed to be a popular book to be published by Princeton University Press, and I hope that some of you would be interested after hearing this talk. When I give this talk to a popular audience in the United States, I ask them to find E equal to mc squared. This is the page from Einstein's famous paper. But this most famous formula in physics actually was not in Einstein's original paper. He didn't have that. He didn't have the idea. This only appeared only a few months later. And Einstein also wrote to a friend after writing this paper. He was very worried that the result is incorrect. And he said, the argument is amusing and seductive, but for all I know, the Lord might be laughing over it and leading me around by the nose. So I asked the lay audience to find E equal to mc squared on this page, and of course they cannot find it. But you guys are mathematicians and physicists, and so you guys probably find it right away. It's, of course, this formula here. And I give you a hint. Capital V is c. In Einstein's paper, speed of light is not called c. That's a later thing. And E is not written as E. E is written as L. Okay? And K is the kinetic energy of a moving body. Okay. All right. So I want to emphasize 2 points of Einstein's work. Einstein's work had major impact on physics because Einstein showed that physics no longer have simultaneity. Now, this loss of simultaneity is extremely important. It made physics local and not global, because the conservation law that we talked about before could be global. You know, an electric charge could disappear in Beijing and reappear in Timbuktu, reappear in Timbuktu in Africa, and charge is perfectly conserved, okay, if simultaneously. But in Einstein's theory, in relativity, there is loss of simultaneity. So you cannot say the two events occur simultaneously. If a charge could disappear in Beijing and reappear in Timbuktu yesterday, so this would violate all kinds of common sense ideas about physics. So this makes physics local rather than global. Okay, it has to be, the conservation has to happen at the same point in space and time. The other thing about Einstein is that he moved from the exterminator relativity to the choreographer of space-time, because he noticed that Newton's law of physics is not invariant under Lorentz transformation. Okay, now we come to number 7. My book is very simply organized because it only has 10 chapters, and each chapter is an idea. Number 7 is the idea of that the forces in the universe are unified. So this drives towards unification, as I said, started with Newton, who unified terrestrial mechanics with celestial mechanics. And then Maxwell and his contemporaries unified electricity and magnetism. The unity is certainly not far from obvious. It's certainly far from obvious in everyday life. Light and sound seems to be completely different, and but they're ultimately both due to electromagnetic interaction. In the United States, the fact that light and sound seems to be completely different, sometimes used as a basis of a joke, which is, how do you tell somebody's an idiot? Because he could emit sound but not light. So, so the unity of forces towards the end of the 19th century into the 20th, this is from my book, one of my earlier books, and you see that Newton, the celestial and terrestrial mechanics used to be different subjects, and it got unified, and gravity and acoustics was the theory of sound. It became part of mechanics, and optics became part of electromagnetism, but mechanics then become part of electromagnetism, electricity and magnetism. And Einstein, he hoped but failed to unify electromagnetism and gravity. And why did Einstein fail? Because there's some stuff lurking in the corner. And Einstein totally ignored all this. And he thought this is just some trivial details that could be left alone. And it's the weak and the strong interaction lurking in the corner, radioactivity. Okay. So now our picture is changed from the end of the 19th century into the 20th. And now this is the picture of the unity of physics around 1985. If we believe in grand unified theory, then there are only two interactions left to be unified. So, in particular, I point out to you that the corner that Einstein ignored became the weak interaction and the strong interaction. And then electromagnetism, instead of being unified with gravity, was unified with the weak interaction, become the electro-weak interaction, which then get unified into grand unified theory. And we hope that the gravity and grand unified theory could be unified into a superstring theory. Whether or not that could happen, we don't know. Okay? So, this is from my book, which is around the time when Ed Witten came to Santa Barbara and told us that everything you guys are doing is totally off and ancient, and you should all start doing string theory. Okay. So, now I come to number 8 in my book, the 8th great idea in physics. And this, I think, at this particular Congress, some people are particularly interested in, which is the relationship between mathematics and physics. Well, we all think that the Creator speaks the language of mathematics. And this idea goes back to Galileo, right? Galileo said that the language of the universe is written in the mathematical language. And that's what every physicist believed in until Eugene Wigner came along. And he wrote a very important essay, which is called, with the title, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Well, opinions differ. Wigner's remark, some people think Wigner's remark is trivial, and some people think it's profound, and some people think it's both trivial and profound. I happen to think it's profound. Now, why should this be so? And in fact, physicists have debated about this. Why is mathematics relevant to physics? And at the 50th anniversary of Wigner's paper, there was a book edited by Ron Mickens, to which many physicists and mathematicians contributed essays, many famous mathematicians. I contributed an essay called The Unreasonable Effectiveness of Symmetry in Particle Physics. And incidentally, in preparing this talk, I looked up Wigner's paper, and I found it surprisingly. I have always thought that he said physics, but somehow he said natural sciences. I don't know why. Because what does he know about the other sciences? He was a physicist. And as far as I know, math doesn't play a prominent part in biology, except perhaps in the construction of phylogenetic trees. Graph theory may be used a little bit, certainly not in geology as far as I know. So I'm surprised by the actual title. Now, we all know, everyone in this room knows that physics and mathematics grew up together, and they were intertwined until they grew apart again towards the end of the 19th century. And one of the many reasons is the rise of rigor, which even the likes of Hermite, the French mathematician Hermite, which in physics we know as Hermitian operators and Hermitian matrices, denounced, right? And which Einstein referred to as more or less dispensable erudition. But with string theory, they're coming together again. And physics needs mathematics, no question. Before string theory, the last three major episodes in the history of physics, and I only talk about the major episodes, and I listed three. They are the partial differential equations for electromagnetism, differential geometry for gravity, and group theory, group representation theory to be exact, for quantum mechanics and particle theory. But it's striking that for most purposes in physics, other than proving rigorous results, Mother Nature seems to have taken only the first few weeks of an undergraduate level type course in each of these subjects, as far as physics is concerned. So I'm, of course, speaking only of the working class of theoretical physicists, people that belongs to the working class, and people namely like Feynman. Okay, and as I already said, I belong to the so-called Feynman school, and I belong to the working class. So these are my teachers and the people at Princeton and so on. And there's no question, of course, different parts of physics need different amount of mathematics. Some parts of physics need a lot of mathematics, such as string theory. And there are parts of physics that need very little mathematics. So I can think of, for example, astrophysics, the actual work of understanding galaxies and stars and so on. So the other thing that is interesting to me is that in the vast ocean of mathematics, my impression, at least from talking to mathematicians, is that only an infinitesimal bucket, a really, really tiny fraction, appears to be relevant for physics. Somehow, in this ocean of mathematics, most of it hasn't proved to be relevant. So at least thus far. So maybe the future would be different. So for example, in the 1950s, confronted by seemingly unsurmountable mysteries, so we have to go back to the 1950s, remember, when all kinds of new particles were discovered and so on. So some particle theorists naturally hoped that advanced mathematics would come to the rescue. But in the end, through electroweak unification, quantum chromodynamics, and quantum and granulified theory, it was by and large not really needed. As I said, only the first 5 weeks of group theory course that I taught to undergraduates. Maybe Lie algebras up to SU3, SU5, perhaps SO10. And since mathematicians are in the audience, I also give the translation because the dictionary, we need a dictionary because the notation used by physicists and mathematicians are different. And what physicists call SU3, SU5, and SO10, mathematicians call A2, A4, and D5. So time and again, in various contests between people in physics, between physicists in trying to understand something, self-proclaimed mathematical ignoramuses, such as Gell-Mann. But I don't believe him. He constantly claims he doesn't know any math. And Feynman does the same. But I don't believe these people. So they would triumph over people who knew much more than him. That's what Gell-Mann keeps saying. So much of physics is now charging forward with little need of mathematics. As I said, it depends on the field. Some areas of mathematics, some areas of physics need a lot of mathematics, and some appears to need very little, such as cosmology and atomic physics. While particle physics, or what I would prefer to call fundamental physics, appears to be stuck. So right now, we don't know how to make progress. And perhaps a tidal wave of mathematics, some even unknown to mathematicians, has to wash over physics. Or perhaps physicists have to work through their own problems, as in the 1950s when experiments were plentiful. So who knows what would happen, whether physics would need a tidal wave of mathematics or not. So nobody knows. And here I can only quote a wise man, a very wise man, namely Zhou Enlai. So I quote Zhou Enlai when Henry Kissinger asked him a question. Zhou Enlai said, "Only time could tell." So now I come to number 9, and on my list, which is entropy and thermal agitation. It's all about sharing. Somehow in the universe, different systems have different amounts of energy, and they all want to share this energy with each other. Okay? And this involves entropy and thermal agitation. Joseph Fourier, he's I would call him a 18th century More is different guy. Like Anderson is the 20th century More is different guy. So recently, a friend of mine, Professor Phillips at Caltech, he sent me Fourier's treatise on heat. And in the preface of his treatise, Fourier said something like, well, that guy Newton was great. He's a smart guy. He's with a system, the world. We now know how cannonballs and moon move. But poor me, he's done all the famous things. What do I do? So I still have to figure out what is hot and cold. And yesterday, somebody mentioned that the young people on my panel that I moderated, some people mentioned young people often feel that all the great things in physics has already been done. So I want to tell you that Fourier felt the same way, that Newton did everything already. But among other things, by working on heat, Fourier showed that functions could be represented by sums of sines and cosines, which is certainly a great mathematical contribution. And he also insisted on the left and right-hand side of the equation must have the same dimension. Then our next great man is Rudolf Clausius, the German, who introduced the concept of Verwandlungsinhalt, which means transformation content. But mercifully for us, he later changed it. He had mercy on us, and he changed it to the word entropy, which is how we know it. Entropy is a very nice word. It has many cognates, words that are related to entropy, namely tropical, for example, and zoetrope, which is a early precursor of movies. So, in fact, the zoetrope is a very nice word because tropical means transforming and moving, and zoe is like in zoo and zoology, it means life. It means things come alive when it's moving. Okay, so I like this word much more than the American movie. It's a terrible word. Okay, so our next great hero in this list is Ludwig Boltzmann, who, because by studying entropy in the second law of thermodynamics, he discovered a microscopic world. And then next, Claude Shannon, of course, the concept of information by introducing the concept of information and its connection to entropy. So I recommend to the audience here the movie, the Bit Player, which I believe is a free movie streaming on the web, about his rather tormented life. For example, to show how he's tormented, he's the only member of the Institute for Advanced Study in the history of the Institute for Advanced Study to quit after 6 months. This was unheard of. He simply quit. Okay. In fact, his wife thought he was going to his office at the IAS every day. But turns out he wasn't. He was just wandering around Princeton. And so now all these people, these 4 guys, introduce entropy. And now entropy of black holes and information content, as many of the people in the audience knows, are probably the most substantive handle we have on quantum gravity. So it's by studying entropy and information content in black holes, we may make progress. So now I come to number 10. Number 10 is just physics and action. I find it very miraculous, almost unreasonable. But the same physics could have different formulations. So the classic example is, of course, Fermat's least time, thank you, versus Snell's law versus Maxwell's wave. And then Newton's equation of motion versus Euler-Lagrange. And Hamilton's formulation. And, when I was a student, I asked my professor, why? Who needs Lagrangian? Who needs Hamiltonians? I don't need any of this. Once I learned Newton's equation of motion, I thought I could solve all the problems. So, and in fact, classical physics, we don't need Lagrangian and Hamiltonian, and it's only with the coming of the quantum. And as you know, quantum mechanics, you need the Hamiltonian. And the Hamilton comes in and gives Schrödinger's equation. And then Dirac and Feynman asked the question, why is the Lagrangian doesn't come in? And Lagrangian is, in fact, became the most important because in relativistic theory, the Lagrangian is a scalar, while the Hamiltonian is not. And this led to the Dirac-Feynman integral formulation. And so I always thought it's a mystery. All the empirically established physics up to grand unified theory could be derived from an action principle. Why? Is this a mystery or not? So I think it's a mystery. I don't know why. You can certainly write down equation of motion that cannot be derived from an equation of motion. From an action principle. So, but there's something deep in mathematics that tells us that every laws of physics that we know at the fundamental level can be derived from an action. Why? We don't know. Okay, so I finished my talk, but I would like to ask you to indulge an old man, namely me, with my memories. So I'd like to show you a few photos that might be of some historic values. I was born in China, but I left when I was very young, when I was a child, with my parents, who eventually emigrated to Brazil, where I grew up. And so the first time I came back to China was 45 years ago. So it's unbelievable what has happened in these 45 years. At that time, China was just coming out of the Cultural Revolution. And 45 years later, we see these incredible cities and buildings and so on and so forth. And so I'd like to show you a few photos. And here you see Professor Yang standing there. And here I am after my talk. And then at the end of the conference, they gave me this scroll describing the style of my talk. And here's a picture of me with T.D. Lee and his late wife, Juliet, who has since passed away, I guess. And then here's another photo with Yang Zening, Xian Yang. And some of you may not recognize Chen Hongmo, and Florence Zhang. And Florence and Chen are both at Oxford. And finally, I had the good fortune of meeting the supreme leader. There's me with Deng Xiaoping. And, without this great leader, China is unthinkable. I cannot imagine what China would have become. It would certainly not be, we would not be here standing and talking in this conference. So, thank you very much.
Thank you, Tony, for giving us such a